Hi, this video is about universal differential equations. This is not just a pure mathematical concept like partial differential equations or ordinary differential equations, but this is a powerful concept from the domain of scientific machine learning. So we will look at how you can combine your knowledge, your scientific knowledge or physical knowledge of a system with the power of neural networks to make very good predictions, right? So that is what UDE or universal differential equations are about. So neural networks are essentially black boxes because you don't know what is going on inside them. You know the weights, but it's very hard to interpret them. So you also know that there is this theorem called as universal approximation theorem. For those of you who probably have not heard of this, it is a theory that suggests that a neural network with a single hidden layer of finite number of nodes can pretty much approximate any continuous function in a given range of input. So because of this, even if your data, your input data or the experimental data is completely weird, your neural network will fit through that also. Look at this example. So in this plot on the left-hand side, I have plotted height versus time for a ball that is thrown up. So the height increases, reaches a maximum point, and then the height decreases with time, right? So here, if you train a neural network, it can match the experimental data really well. That is what is demonstrated with this blue circles and yellow dots. But imagine that the person who was making these height measurements made a critical experimental mistake, or maybe the instrument that was used for measuring the height itself had some fault, and the experimental data happened to be such that one data point is here instead of it being here, it happened to be here. Then what will neural network do? Neural network is good at approximating this also, unless we do something to take care of these outliers or randomness in the data. So neural network can approximate this also, and this is a problem. So because here the neural network is essentially deviating from the physics, because physics predicts that the height should vary as a quadratic function with respect to time, whether the ball is directly thrown up or whether it is thrown like a parabola. So, you know that neural networks are very much capable of making predictions that can violate basic physical laws or even laws of thermodynamics. All of these things can happen by just using neural networks. So machine learning scientists have recognized this as a big problem. And what they did is they introduced a concept called physics-informed neural networks. This video is not about physics-informed neural networks, but this PINNs or physics-informed neural network is a way where you can penalize the neural network whenever it makes a physically nonsensical prediction. So what you do is, let's say the height h cap is the height predicted by the neural network, and let's say h is the actual height. Then you look at the difference between these two heights, and for different time points, you look at h cap I versus hi, look at the difference, square it, then you sum it from I equal to 1 to n if you have n data points, and do 1 by n. So this is the normal mean squared error loss. In physics-informed neural networks, what we do is we add some additional loss terms. Like one term could be the loss due to the d by dt. So the physics can say that dh by dt, this is the velocity. It is initial velocity minus gt. So you can have a predicted dh by dt at time ti and an actual dh by dt, which is available from this equation. And you can have the square of this for different time points, sigma I equal to 1 to n. That could be one second loss term. There could be one more loss term to cater to the initial condition, where you have predicted height at time t equal to 0 minus the actual height at time t equal to 0. So this is the initial condition. So you look at how much your predictions are varying from the initial condition. So this is the way in which PINN was penalizing the loss function for deviating too much from physics or deviating too much from the experimental data. If you deviate too much from the experimental data, this term will be big. If you deviate too much from what the physics is predicting, these terms will be big. So this is PINN in a nutshell. But there is a problem. Because what if you don't know the full physics of your system? What if you don't know whether there is some air drag or some kind of wind or some other force acting on the ball that is thrown up? You don't know that. In that case, how do you penalize the neural network? For this, an initial setup that was built was you completely ignore the physics. You simply set up a neural network which can make a predicted dh by dt. So there was a concept called neural ODE. I'm not going to the details of that, but basically neural ODE is a system where you predict a dh by dt, and then using this predicted dh by dt, you can integrate to obtain a height at a function of as a function of time. So you can integrate it numerically instead of actually mathematically integrating to get some predicted height at a point of ti. Then you compare this height with the actual height. So you look at then h cap minus h, and then you use this to modify the neural network weights. So this was called as neural ODE. But in neural ODE also, the partial knowledge of the physics of your system is not coming into the picture. So neural ODE is one extreme where you take no physics into account. PINN, physics informed neural network, is another extreme where you kind of assume that you know the physics very well, but mostly you will be somewhere in between. So now let us come to universal differential equation, which is the best of both worlds, where you can utilize your knowledge of the partial physics of the system and the knowledge or the fact that neural networks can approximate whatever knowledge you are lacking. So that is UDE. We can understand UDE with a very simple example. Here is a spring mass damper system. So a spring mass damper system, if you plot the amplitude of the vibration of the spring as a function of time, so here x-axis, y-axis is kind of amplitude and x-axis here is time, the amplitude will die down because of presence of a damper. So actually the way you draw this is something like this. So you have a spring, you have a mass here, and you also have a damper, and the presence of this damper will dampen the vibration amplitude. So initially you will give the mass some sort of displacement, and you will have a displacement, you will have a velocity of the mass, you will also have the acceleration. Then you say that the force acting on the mass m, so you will know the mass, you will know the spring constant k, you will know the damping coefficient c, and then you will say F, which is equal to MA. MA is what? Mx double dot. And this x can be measured from here also. This x can be based on any origin. So if this is your origin, this is the x. Mx double dot equal to minus kx minus cx dot. So this is the spring force due to spring Fs. This cx dot is the damping force due to the damping mechanism. And this is the acceleration. So force of acceleration or inertia. And then you can say that mx double dot plus cx dot plus kx equal to 0. You can bring all of this onto the one side of the equation. So this becomes md square x by dt square plus c dx by dt plus kx equal to 0. So this is the inertial term, this is the dampening term, and this is the spring force term, right? 3 terms. And just notice what kind of equation is this. This is a second order ordinary differential equation. Second order because d square x by dt square is the biggest derivative term. And this is ordinary differential equation, not partial differential equation, because the x depends only on time t. So you don't have partial derivatives like dou x by dou t. There is only one independent variable, that is time. So this is a second order ODE. Now, normally, if you are conducting experiments, you will know the mass, you can measure, you can know the damping coefficient, you can also know the spring constant, and then experimentally you could measure the displacement x. But in an ideal system, if you have the knowledge of the mass m, c, and k, and if you also know some initial conditions, then you can fully solve this system of equation so that you can predict x of t. Basically, position as a function of time you can predict. You may need two initial conditions. I mean, you actually do need initial conditions too. One of them could be x of 0. So position at time t equal to 0, and another is x dot of 0. So x of 0 is where the position of the mass is at time t equal to 0. X dot is what is the speed of the mass at time t equal to 0. Because this is a second order ODE, you need two initial conditions to solve this. Now, what happens in a real life situation could be very different. Let's say there is a car, and this car has like some kind of this spring mass damping system in its suspension. So let's say the spring mass damping system installed inside the suspension is something like this. And there are 4 wheels, right? So let's say the total mass of the car M that is known, each wheel is probably carrying M by 4. So there is a mass of M by 4 here. This is an oversimplified version. I'm sure this is not exactly how you have to draw it. But let's say you have a mass M by 4 and then you have a spring of known spring constant. So let's say you purchase the spring from a very good manufacturer. So you know exactly the spring constant, but let's say you purchase this damping system from a very bad manufacturer. So you don't know how exactly this damping mechanism works, whether it is behaving linearly with respect to the velocity or whether it is something else. You have no idea, let's say. Now, the goal of this system is if the car is moving and if it is entering into some gutter, the role of the spring here is to make sure that the immediate jerking motion is not happening to the car, because spring will smoothen it out a little bit. The role of the damping mechanism is that once there is some delayed jerking motion of the car, it should not keep on oscillating back and forth. The oscillations should die down, otherwise the passengers will feel dizzy or it won't be very comfortable. So you should have appropriate spring mass damping system in cars. So in the most simplified way to explain, to have a comfortable ride. Now imagine you are in this kind of a case where you know these two terms. You know the md square x by dt square term. And let's say, you have the mass with you. You know the spring constant term associated with it, so kx term. And you don't know this term. You have no idea what is going on with the damper. So you don't know whether it is c dx by dt. You don't know whether it is some other constant multiplied by dx by dt, the whole square. Nothing. You don't know anything. Because in real life, the damper might be non-linear. It could be sinusoidal of velocity. Who knows, right? It could fluctuate with the temperature inside the damper. So all of these things can happen in a real life. So how can we now solve this equation where you have mx double dot plus kx plus unknown term, some unknown term for damping equal to 0? What would you do? So here you have partial knowledge of the physics because these two terms are known. What would you do? Are you going to say that, no, I'm not going to take any of this. I will simply look at my experimental data of x as a function of time and maybe x dot as a function of time. I will look at the experimental data for both of these and I'll try to fit a neural network through this data. So x as a function of time might be like this. X dot as a function of time might be like this. And now I'm saying that I'll fit a neural network so that it can learn from this data. Is that what I'm going to do? Or should I also consider the fact that I know partial physics in this system? This is where UDE actually enters the picture. Universal differential equation can combine your partial knowledge of physics. So this sentence I only wrote, but basically I have took the screenshot from my Substack article based on this. I will share the link to that in the description. But basically it's like the UDE is saying, I know some physics, so I'll use that. But remaining terms, there are unknown terms. So that I will replace with the neural network. So how does that happen? That is like this. So this unknown term, other than md square x by dt square and kx, the unknown term you replace with a neural network. So what exactly does this replace with neural network mean? What is that? It means this unknown term will be, the value of the unknown term will be whatever is the value of the output of the neural network. So a neural network with some input, I'll tell what the input is, but some input that will output some number. That number will represent the value of whatever the unknown term is. That is what's happening here. So if you truly think about it, this is like a hybrid model where you have some unknown science or unknown physics happening, but you are using a neural network to learn that physics in tandem with the known physics. So you have known physics, then you have unknown physics, but you make use of your knowledge of the known physics, and then you make use of a neural network to predict the unknown to see if you can overall get a very good prediction. That is what we are going to do here. So in the ordinary differential equation, originally we knew all the terms, but here this is not an ordinary differential equation. If you look at this fully, it's also not a partial differential equation. It's a universal differential equation because it also has the presence of this neural network, which is like a universal approximator. So these systems can approximate pretty much any physical phenomenon or any phenomenon that is governed by an ordinary differential equation with unknown parameters. So the rest of the terms are part of a ODE, but this is unknown parameter. But combining these two, you can universally learn pretty much any phenomenon. So now what do we do here? We define the neural network, right? So this neural network should have some inputs. So the input in this case will be, potentially there are three inputs possible. One is the time itself. So you provide the timestamp. Second is the x, the displacement as a function of time. Third is the velocity of the motion of the mass as a function of time. So with these three things as the input, the neural network will have certain parameters, weights, biases, and what all the parameters, whatever else will be there. Maybe hyperparameters are also what activation function you are going to use in the neural network, etc. So all of that is kind of embedded here. The parameters especially is embedded here in this term phi. So what you are now going to optimize is, you'll be optimizing this phi such that your actual value of mx double dot plus actual value of kx plus predicted value of the damping force by the neural network, all of these things should sum up to 0, right? If it is not summing up to 0, it means your neural network is making some mistake. So if your friction is not of the form c dx by dt, meaning if the damping is not of the form cx by dt, c dx by dt, that means it's very difficult to come up with a form of equation. You don't know whether it depends as a square or cube or some higher order polynomial or something. So you are filling the gap with a neural network. So how does the neural network make predictions? How does the universal differential equation make predictions in this case? So think about what goes into the input and what goes into the output. Here, the neural network, is it predicting the displacement directly? This neural network term, is it predicting displacement directly? No, it is not predicting displacement. It is predicting some force term. So the unit of this is Newton, right? This is force. This is also force. So this is like F equal to ma kind of term. This is like F equal to minus kx kind of term. So whatever is the prediction of the neural network, it is a force term. It is neither displacement nor velocity. So how does the UDE, is this neural network now the UDE or is it something else? So this neural network alone is not UDE. UDE is the entire system in which one more component is there, I will show you, which solves for the displacement or the velocity of the mass. Then you can compare the predicted velocity or predicted displacement with the actual velocity and actual displacement that you know from your experimental data. All right. So what does your experimental data look like now? An experimental data for displacement would look something like this. If you actually solve the differential equation, you will get smooth curves like this. The mx double dot plus cx dot plus kx equal to 0. If you solve this differential equation, you will get this smooth blue curve. But in reality, you will never get something like this from experiments. From experiments, you may get these yellow dots for the real x of t. Now, you may have a similar data set for velocity, perhaps. So when the displacement is maximum, velocity will be minimum. Then the velocity will be like this. It will peak when the displacement is 0. So here velocity will be minimum. Then here the velocity will be peaking. Here it will reach a minimum. Then here it will peak. So the velocity will look somewhat like this. So there will be a 90-degree phase shift sort of between the velocity and the displacement. So you could measure the real value of the velocity. And that will also be like these dots, the noisy velocity data set. And you also have the noisy, these yellow dots. These are the noisy displacement data set. Now, this is the experimental data. Now you are going to train a universal differential equation model on this data set so that that model can now, as a combination of physics and neural network, can make good predictions. So let us see how to do that. So please understand that the neural network part of the UDE is not predicting displacement. It is predicting the force. It's predicting sort of like the damping force. So how can you make UDE predict x of t or x dot of t if UDE is just predicting force? This is how it is. So a UDE architecture involves neural network plus something called as numerical integration. So what happens is you have experimental data, right? So you have x of t versus t. Maybe you also have velocity as a function of time. So let's say velocity as a function of time is something like this, or not like that. Something like this. I'm drawing it very poorly, but let's say you have x of t and x dot of t both. So you will have data point for a given time point. You will have the displacement data and you will have the velocity data. This is experimental data. Now, if you were using a black box neural network, you can easily fit it through either of these experimental data points. But you are not going to do that because you have knowledge of the partial physics. You know that the motion is in the differential equation term. There is mx double dot plus kx term. You know that there is the presence of these two terms. You just don't know the presence of you just don't know what is the damping force looking like. So the input to this neural network could be time. So this is initial condition is not needed if you are already passing the displacement as a function of time. So you will be passing displacement as a function of time. You will be passing velocity as a function of time. You can also pass time itself, but in the example that we are going to implement, we will not be passing time. You can simply, with just x of t and x dot of t, you can train the neural network to predict the damping force. So now with the input data, which is the experimental data, a neural network will be trained to predict the damping force. Now, what do you do with this damping force? This damping force is now the output of the neural network represented as n and theta. So that is n and theta. Here, in addition to the value of this term, if you will also use m d square x by dt square and kx, and you will perform a numerical integration to predict the value of x. How do you do that? Very simple. So if you have a spring mass damping system, and if the displacement, let's say you are looking at t equal to 0, and let's say at this point the position x equal to let's say 1 meter. I know this is a big number, but this is just for the ease of calculation. And let's say the velocity x dot equal to let's say this is 0.5 meters per second. So now what you want to do is numerically integrate this to get x of t plus delta t in the next time step. And you also want x dot of t plus delta t. How do you do that? You can, this is the simplest numerical integration, which is Euler method. So x dot of t plus delta t equal to x dot of t. So here t equal to 0, by the way. So this will be x dot of t plus x double dot of t times delta t. So what does this mean? This is like velocity at time delta t. So t equal to 0, you can substitute, equal to velocity of time t equal to 0 plus x double dot is acceleration. Acceleration at time t times delta t. And what is this? Velocity at time t equal to 0 is given to be 0.5 meter per second. So this will be 0.5 plus acceleration. You have to look at the term m d square x by dt square plus kx plus neural network theta. So let's say you know the mass m to be 1 kilogram. Let's say k is also it is Newton per meter, right? So let's say this is 1 Newton per meter, and d square, and let's say the neural network, the prediction made by the neural network is let's say 5 Newton, because this will have the unit of some sort of like a force. Now, what is d square x by dt square based on this equation? D square x by dt square, according to this equation, should be 0 minus nn theta minus kx divided by m. right? If you look at this equation. And what is this? 0 minus neural network output is what? 5 Newton. 0 minus 5 minus kx is 1 times 1 meter. So minus 1 divided by mass is also 1. This is equal to minus 6. So here this is minus 6 multiplied by, so let's say delta t equal to 0.1 second. I'm just taking assumption. So this is 0.1. Now what will this become? 0.5 minus 0.6. And this will be minus 0.1, right? I hope I'm not making any calculation mistake. Now with this velocity, we can calculate displacement. So x of t plus delta t equal to x of t plus x dot of t times delta t. I'm using the simplest Euler integration. I know that there are better methods like fourth order Runge-Kutta, etc. But just let's keep it very simple. So now x of delta t is equal to x of 0 plus velocity at time t equal to 0 times delta t. And this would be, in fact, here we can use velocity at time t equal to 0 or the average velocity at t equal to 0 and t equal to t plus delta t. Anything we can use. And this will be x of 0 was initial position 1 meter, 1 plus velocity was 0.5 meter per second. So maybe we can use that 0.5 meter per second times 0.1. And this will be 1.05, right? So this will be the new position. So now you have the x of the next time point. So ti equal to 2 is equal to 1.05, and x dot at time ti equal to 2, the next time point where I equal to 2 equal to minus 0.1. Now this is the output you obtain here. You obtain the predicted value of x and predicted value of x dot. So here you get predicted value of x and predicted value of x dot at time ti. Now you can compare this with something. With what? With this guy. You have experimental x dot and experimental x. So you compare this x cap, x dot cap and x cap with x dot and x. And if the difference is very big, that means your weights of the neural network is very bad. So you have to perform gradient descent and you change the weights. So for that, what you do is you calculate the loss. And loss is what? Loss is equal to xi minus xi cap minus xi the whole square, sigma 1 by n, plus you can add those two if you want, xi dot cap minus xi dot. So predicted velocity minus actual velocity, the whole square, summing it up and averaging it out. So this can be your total loss. Now you can do dou loss by dou weights, which I am generalizing as dou loss by dou theta. So theta is the parameters of the neural network, this theta, which means now the neural network prediction will change because now I'm going to change the weights of the neural network. How is that changed? Theta new equal to theta old minus eta is the learning rate times dou loss by dou theta. This is the gradient descent. So I will modify the value of weights using the current weights. And this is the learning rate. This could be a constant 0.1 or something. And dou loss by dou theta is where I'm utilizing the output, because the output will determine how much the loss is, the difference between your predicted output and the actual output. So using this, I can modify the neural network to make new predictions. Using the new prediction of the damping force, I can using the formula, I can recalculate a new predicted velocity and new predicted position displacement, compare again with the experimental data, and do this for all the experimental data points to get the total loss, not just for one data point. I showed the example for one data point, but you will be doing it for all the experimental data points. Do this until the combined loss due to all the experimental data points is minimized, so that you are making good predictions. And that is when you know that your neural network, your universal differential equation is making very good predictions and it is learning the phenomenon. Now here, we wrote this term, right? We wrote the neural network of phi or theta. So in the bottom figure, I use theta instead of phi. So please don't get confused. But what we wrote was that, this neural network term is just this much. Whatever is there in this red box is the neural network prediction. But is that the final prediction that we want? No. So this is the n theta or phi part, okay? But the final prediction, what we want is this. And for that, we are performing this numerical integration using Runge-Kutta method. I demonstrated using Euler method for the simplicity, but you can use more complex or more efficient as in more accurate numerical integration method. And at the end of this is when you get the prediction. So UD is a combination of this neural network plus numerical integration. Okay. Now this would become a neural ODE if you did not know this physics. If you had ignored this physics completely, then you could have a neural ordinary differential equation. So, but here the physics is embedded, but how much of physics? Just part of it. You don't know the damping force. That is why this is called as a universal differential equation. Okay. So just to reiterate the steps which we did. So the first step was initial, the experimental data, initial condition we may or may not use, but basically experimental position and velocity. We feed that into the neural network so that neural network can predict the unknown damping force term. So FD is predicted by the neural network as n theta. Then you combine the unknown term with the ordinary differential equation. So mx double dot plus kx plus neural network prediction. So you combine this, then you numerically integrate to get the prediction. So this is done using fourth order Runge-Kutta or something, or any method, any good numerical integration method. Then you have predictions of x cap and x dot cap. So this is the predicted displacement and predicted velocity. Then you compare this with actual x and actual x dot, and the difference between the predicted and the actual will lead to loss. If loss is very high, you have to modify the weights. So you do backpropagation and you do optimization of the weights of the neural network until, and you have to repeat this, right? So then you again go back to experimental data, make a new prediction, combine the prediction with the known terms, make a new numerical integration, perform a new numerical integration, then make a prediction on position and velocity, again compare, see how much the loss is, and do this multiple times until the loss is minimized. Once the loss is minimized, you have your final model, final UDE model. Okay. So this is the universal differential equation framework. So now what we are going to do is let us solve this actual spring mass damping system using UDE framework in Python. I will introduce you to the packages used for this, but essentially what we will be doing is we will first make noisy experimental data. Here I am plotting only displacement as a function of time. I have not plotted velocity as a function of time, but you can also plot that if needed. But the experimental data will be obtained by first solving the entire ordinary differential equation. So solve the mx double dot plus bx dot plus kx. Just assuming you know b, k, and m, you solve for this equal to 0 to obtain this green dotted curve that you see here. So this is ideal solution. And then to mimic an experimental data, you add some Gaussian noise or some sort of noise on top of it. So those are these red data points. So we will not be using this green curve as our ground truth. Green curve is just used for making the noisy data, noisy experimental data. So this will be our ground truth. And we will be making predictions of displacement and velocity using UDE. And here you can see that the prediction is not that ideally matching with the actual ground truth. Actual ground truth is these red dots. The match is not very good. But when we plot the epoch, meaning number of iterations versus loss, we can see that after around 8 or 10 iterations, your loss is minimizing to a very small number. So here we had run it for, I think, 5 iterations, 5 epochs. So we realized that, okay, we have to run for more epochs. So we run for more epochs and then we plot. And here you can see that the predicted UDE predicted x of t is directly passing through the ground truth data points. And there is a very nice fit. And this is when the loss is minimized. I think here I ran for around 20 epochs. I'll run the code and I'll show you. Before that, let me walk you through the code. So I have already written the code. I have experimented with it and I have ensured that it works very well. So, but I have chunked it into different blocks so that I can explain you block by block exactly what are we doing here. So first we are importing the necessary libraries here required for dealing with numbers and dealing with plotting. And then first we generate the ground truth data. So ground truth data is generated by solving the spring mass damper equation. So equation is here where x double dot is equal to minus cx dot by m, that is this, minus kx by m, that is this. So the equation was mx double dot plus cx dot plus kx equal to 0. Here x double dot you isolate. And then you have two parameters. One is x dot, one is x and one is x dot, right? So this is this y, this is your parameter. And but what this damped spring mass function, this function returns with t as the input and y also as the input. So you have a particular time point and you have y, where y is x and x dot, the displacement and velocity. This function will return the velocity and acceleration. And we need to define the initial condition. So we say the initial displacement is 1, initial velocity is 0. And we are also assuming that mass is 1 kg, k is 5 Newton per meter. The damping coefficient is 0.7. And this is the term which we will assume we don't know, not in generating the true data, but in training the universal differential equation. So we define the time span for which we are doing this. So starting time and ending time, 0 to 10 seconds. And we will be splitting this into 200 data points. Then we solve this equation, solve the x double dot by calling the damped spring mass function. And that is from the starting to ending time. We are passing the initial condition and we are also passing so this is the starting time and ending time, just a matrix which tells you that where is the starting point and where is the ending point. And you are evaluating it over a matrix of this t eval. This is from 0 to 10 in time steps, in 200 steps. Then you have the true x and true velocity. So true displacement and true velocity. That is the sol.y. Sol.y means the solution that is this variable. It holds three things. Inside the y variable, it holds the x and x dot. And inside there is a variable called t. T is the corresponding time for which you are solving the x and x dot. So if you do sol.y, from that you can essentially get x and x dot. From sol.t, you will get the time. And I can show you where we are using this sol.t. But here you have the x value, you have the velocity value. Then you are adding a noise. So the true value of x plus some noise level multiplied by np.random. So this is a random number generator. Then for velocity also, true value of velocity, which is the solution of the ordinary differential equation plus noise level. Now this is your ground truth data. Okay, this is GT, ground truth. Then you simply plot this to get what the ground truth looks like. And then you will get a plot which was shown here, this plot. So I'll run the code and show this to you. But before that, I just wanted to give a code walkthrough. And now we need this package also, torch diffig, for implementing the UD framework. So if you don't have this installed, just install it. I realized it while running the above code, so I had to install it. Then you need the PyTorch. So import the required libraries from Torch. And then we can build a neural network. So neural network is a simple feed forward neural network with displacement U1, velocity U2, and time is optional, as I mentioned. These three are the potential inputs to the neural network. And then it will predict the predicted value of the damping force. So here we have a input dimension is up to 3, but here I think it's only 2 because we can include time, but then the input dimension will be 3. But if you don't include time, if you only include the position and velocity, then the input dimension is 2. Then you have hidden dimension. Hidden dimension is defined to be 16, and then the final output dimension. So in between there are 2 hidden. So the structure is like this. You have one like this. You have a 16 node network here. And from hidden dimension, you have one more like this. And then you have output is a single value, then you have 1. So you have 2 hidden layers of 16 nodes and 16 nodes. Input is 2 nodes, output is just 1 node, and then you have connections from this node to here. I don't think it's fully connected, but basically the nodes in this layer will be connected to nodes in this layer. And then this connects to the final output layer. So 2 units, 16 units, 16 units, and 1 unit. This is the input layer, output layer, hidden layers. Okay. So that is the structure of our neural network. And there is a class spring mass UDE which defines the final predicted damping force variable, damp underscore force, and also putting that into the equation with known terms. So in the known terms, you have kx and mx double dot known. So you can calculate, you can put the damping force to get the acceleration. So x double dot equal to minus kx by m minus f damping divided by m. So minus kx by m is, sorry, not f damping by m. Yeah, correct. So here it is minus 1 by self dot m times damping force. That is this term. And the first term minus kx by m is this minus self dot k minus self dot m times x. So u1 is x and u2 is x dot. So du1 dt is the derivative of u1. du2 dt is the derivative of velocity. So this is now velocity. This is now acceleration predicted by the which you obtain from the neural network output, which is stored in damping force. Here, this is a part which we are already doing before we even pass anything into the neural network, basically converting numpy array. So the noisy x, which is ground truth, noisy velocity, which is ground truth, and the time points corresponding to this x and v are all numpy arrays. Numpy arrays, as we know, is not the most efficient way to pass things into the PyTorch. So this torch-based tensor is the most efficient way to solve, or the most efficient way to handle the data set to be fed into neural network. So we call torch.tensor so that this time displacement and velocity can be converted into PyTorch tensors. Then here is the forward path, right? So first we have the y naught. Y naught is the initial condition. Sol is the solution of the ordinary differential equation, where you have the initial condition, you have the time points for which you are solving using the Runge-Kutta fourth order method. Method also you have mentioned here, RK4, and you are passing the neural network plus ODE framework. So this net ODE is coming from wherever we are calling the forwards simulation. So net ODE, let us go a little bit down to see where we are calling this function forward sim. So forward sim is called over here, right? So if we look at this function, so each epoch, so we have a few number of epochs where we are defining the optimizer, and number of epochs I have mentioned to be 20. We'll be printing the output once in every 5 epochs. We are storing the loss history in this variable so that we can plot loss against epoch, right? So far is fine. Now the solution of the predicted value of x and predicted value of v is stored in this variable so that x pred and v pred can be split into two separate variables. But what is this forward sim inputs? One of the input is UDE. And what is this UDE? UDE is nothing but the output from the spring mass UDE. So in the spring mass UDE, if you go to that class, in the spring mass UDE, you are defining the mass, you are defining the K, you are defining U1, U2, etc. So this spring mass UDE, into spring mass UDE, you are passing mass, you are passing spring constant, you are passing the neural network model, and neural network model is from the damping NN function. So this damping NN is the variable which stores the output of damping NN. This is where the neural network is. So input dimension is 2, hidden dimension is 16. So you had defined hidden dimension to be 16. Now let us check this damping NN once again. In fact, damping NN takes all the inputs. It's a class actually, it's not the function. But in that, we are defining the structure of the neural network. And in that, we can do the forward pass as well. And so the structure of the neural network, I already defined 1 by 16 by 16 by, sorry, 2, 16, 16, 1, the input to output. And Finally, before plotting, I just wanted to go back to this part of the code. Yeah. So here the sol is nothing but the x dot and x. So that is what you are getting. And you are storing the predicted value of solution here, then x predicted and v predicted. Now loss should depend on these two. So loss in displacement is the mean squared error of predicted value of x and the actual value of x. What is the actual value of x? Actual value of x is the PyTorch data set created from the training noisy x data, which we had done here over here. So the training x noisy had converted in as was converted into a PyTorch data set, PyTorch tensor. Training noisy velocity was also converted into a PyTorch noisy v. That is what we are using here. So mean squared error for x, mean squared error for v, and then the total loss is the weighted loss of these two, 0.5 times this plus 0.5 times this. And then we are performing backward propagation by inputting this loss. Optimizer we had already mentioned above here, Adam, with learning rate of 0.01. And then we can append the loss history. So initially loss history was an empty variable, this guy, and we are appending the losses there so that we can plot it for as a function of epoch. So we are displaying here. And then we plot the figure of loss versus epoch. And then the final plot is simply the final prediction. And the final prediction and the epoch plot will look like this. This is the epoch versus loss plot, where you can see the drastic reduction in loss after around 8 or 10 epochs. And after around 20 epochs, you will get a plot like this. So now we can run this on Google Colab. So let's open Colab. And this is the Colab notebook. I will share this notebook link in the description so that you can run it yourself. I have added sufficient amount of theory also in the notebook, so you can read through it and understand. So first, let us run the import packages. And once that is done, it will be creating the synthetic noisy data set. So this is the synthetic noisy data plot. Then the dampening NN, where we define the neural network. And then the output of the neural network is combined here so that you can have a predicted acceleration and a predicted velocity. So then that is this class. Here we are converting the data set into PyTorch tensors. Okay, T eval is not defined. I think the error is happening because I should do this pip install once. So let me first do that. So if you are running in your local environment, you just need to do it once. So torch diff is the package where you can get the UD framework. So for numerical integration, you need this package. So it should not take more than a few seconds to install. Okay, this has finished installing. I'll just clear the outputs. Let us run once again. This is the noisy input data, defining the neural network, defining the part where we combine the neural network output with the known physics, converting to tensor. So you have 200 data points. You are taking 200 data points from 0 to 10 seconds. Then this is where you get the solution. And so here we will, yeah, so this is the neural network, right? Input 2 features. Hidden layer has 16 and 16. Output is 1. Now it's the training loop. So this is quite fast. In fact, we are running only 20 epochs, right? So we'll see the epoch loss decrease drastically, and also we'll see the plot. So I should have printed it once in every epoch perhaps to see the output. So I'll print the loss in every single epoch. So you see it's 0.17, but I think after 10 epochs or something, it drastically reduces. Oh, okay. I have to, okay. The reason why this is happening now is because I did not restart the session. So I'll do that later. Let me first look at the plot. So this is not the epoch versus loss, how it should ideally look like, because if I restart the session, Hopefully all the temporary variables will be gone. Yeah, you see now the loss is high, starting from high, but after even 5 epochs, it's drastically reducing. After 10 epochs, it's very small. Okay, this is good. And now let us, and I think we are overfitting a little bit here because, okay, probably not because this is still training loss. Anyway, so this is the epoch versus loss. And the final prediction will be like this. This is for, we are still predicting for just 20 epochs. So in fact, for 20 epochs, it was not good. So what if this is 100 epochs? We will probably have a better plot. So I think what I have mentioned here, that this better plot is for 20 epoch, I think this is not correct. I think this is for 20 epochs and this might actually be for 100 epochs. I did not note exactly the number of epochs while running. So maybe you have to run 100 epochs to get something like this. We'll see. So perhaps you had to reduce it to 0.002 or something, the error, to get a plot which is of very good fit. Okay, we have finished running 100 epochs and now hopefully the fit is better. I think it's much better now. There is some discrepancy here. Over here also there is discrepancy, but I think it's much better than this fit. This is really bad. So you can play with this a little bit. Try changing the noise level in the ground truth data. Try changing the learning rate. Try changing the number of epochs. I think you will have some interesting results, and see at what point your training itself is breaking. Another thing which you can do is, in addition, is trying to do forecasting. So currently we just did the training from 0 to 10 seconds. You could try forecasting by using only half of this data set for training. So use until 0 to 5 seconds for training. For 5 seconds to 10 seconds, try to do forecasting using the predicted using the neural network weights plus the Rangekuta solver. So just try that. But with that, I think we can wind up this lecture here. I'll be sharing the notes plus also this code with you. Just go through it and let me know what you get. So I hope you understand the basic idea behind UDE, where you are trying to combine the knowledge, partial knowledge of physics, and whatever is impartial, you include neural network to make a good prediction. That is what we are doing in neural ODE. It's very powerful. In fact, it's more powerful, in my opinion, than physics informed neural network. PINN is mostly used as a ODE solver. It's not used as a prediction system, but UDE is the true, I would say, king of all these three methods. If you compare physics informed neural network versus normal neural network versus UDE, in my opinion, UDE is the best. So try this out. This is definitely one step closer into your journey towards combining machine learning and scientific knowledge. So take care until we meet in the next video. See you. Bye.